In this video, we will explore 2 hours of quiet cosmic mysteries, phenomena that continue to puzzle scientists and inspire wonder. From invisible matter to distant signals, each story offers a glimpse into what we know and what we still don't. Write in the comments what time it is for you and where you're listening from. Now, enjoy listening and have a peaceful night.
Dark matter. Dark matter is not what you see when you look at the night sky. It is not the stars, the galaxies, the planets, or the glowing clouds of gas. It is not even the blackness between them, and yet it is there, silent, invisible, and everywhere. It is the structure beneath the visible, the quiet scaffolding of the universe. For decades, astronomers have watched galaxies spin too fast, stars on their outer rims moving in defiance of gravity as we understand it. According to Newton, they should drift away into space. But they don't. They remain bound by something we cannot see, cannot touch, and cannot directly detect. That something is what we call dark matter. It neither emits nor reflects light. It passes through you, through planets, through everything, unnoticed. And yet, without it, the galaxies would unravel like thread pulled loose from a spool. We first suspected its presence not through direct observation, but through behavior. How light bends around massive clusters, how galaxies refuse to fly apart, how the universe expands yet clings together in vast, delicate structures. The name dark matter is a placeholder, a quiet admission of ignorance. We know it exists because of what it does, not what it is. It has mass, but no glow. It shapes the cosmos, but leaves no fingerprints. Imagine something that fills the space between the stars, that drapes itself across galaxies like an invisible web, a hidden network of filaments holding everything in place. Some say it could be made of undiscovered particles, WIMPs, axions, sterile neutrinos. Others wonder if our understanding of gravity itself needs to change. For now, the mystery remains. We live in a universe where most of the matter is unseen, where the dominant force in the structure of space is quiet, indifferent, and veiled. And as you drift to sleep, consider this. The stars you see are only a sliver of what holds the cosmos together. The rest moves silently, patiently, holding the night in its invisible hand.
Dark energy. Dark energy is not something you can hold or even imagine easily. It is not matter, nor light, nor any known force as we experience it. And yet, it is the quiet engine that drives the universe apart. Unlike dark matter, which pulls, dark energy pushes. It is the hidden breath behind cosmic expansion, an invisible pressure woven into the very fabric of space itself. In the late 1990s, astronomers studying distant supernovae noticed something unexpected. Instead of slowing down, the universe was expanding faster than before. Galaxies weren't just drifting apart, they were accelerating away from each other as if pushed by some vast, unseen hand. This wasn't supposed to happen. Gravity should slow things down, even if only slightly. But something else was at work. That something we named dark energy. We don't know what it is. We don't know where it comes from, but we believe it makes up nearly 70% of everything. Not just everything we can see, but everything that is. It is not a substance in space, it is a property of space. As the universe grows, so does the amount of dark energy. The more it expands, the more it accelerates. Like a soft, endless exhale, it stretches the cosmos with silent insistence. Some believe dark energy is the cosmological constant Einstein once theorized, a small, stable energy present even in a perfect vacuum. Others think it may be something dynamic, evolving with time, a shifting energy field that shapes the ultimate fate of the universe. Perhaps in the far future, dark energy will stretch space so rapidly that galaxies will vanish from sight. Then stars, then atoms, until all that remains is cold distance and silence. As you lie still, letting your thoughts slow, consider this. The emptiness around us is not empty at all. It is filled with something quiet and persistent, softly unwinding the universe in every direction. Dark energy does not roar, it does not flash, but it is always there, humming just beneath the surface of space itself. The fate of the universe. The universe had a beginning, a flash, a breath, an expansion from something smaller than a grain of dust. And now it continues to grow, stretching silently in all directions. But like all things, it must one day face an end. The question is not whether the universe will end, but how. The first possibility is the Big Crunch. In this scenario, gravity will one day overcome expansion. Galaxies will slow, stop, and begin to pull back together. Over billions of years, the universe will contract, folding in on itself until everything collapses into a single point, a reverse of the beginning. But signs suggest the opposite is happening. The second possibility is the heat death. As the universe expands, stars will burn out, matter will decay, galaxies will fade. The distances between everything will become so vast that no light will ever reach another point. In this distant, unimaginable future, all energy will spread thin. No temperature difference will exist, no motion, no life, just silence. And then there is the Big Rip, a more dramatic ending. If dark energy becomes stronger over time, its repulsive force might not just separate galaxies, but rip apart stars, planets, atoms, space itself. In the final moments, even the fabric of time may unravel. Each of these outcomes depends on forces we barely understand. How much dark energy exists, how it behaves, whether it changes, whether gravity holds or breaks. We live in a moment of balance between a past of fire and a future of uncertainty. As you rest, breathing in the stillness of now, know that the stars above are part of a journey that began in brilliance and may end in quiet. Whether with a crunch, a whisper, or a tear, the universe moves forward, and we, small, listening, wondering, move with it. Planet 9. Far beyond Neptune, past the icy fragments of the Kuiper Belt, there may be something hidden in the dark. A planet, massive, cold, and unseen, circling the sun in silence. Astronomers call it Planet 9, a hypothetical world perhaps 10 times the mass of Earth, drifting on a slow, elongated orbit that could take tens of thousands of years to complete. We've never seen it directly, but its presence is suggested by the way other objects behave, how certain distant bodies cluster, how their orbits tilt in strange alignment, as if something large and distant were pulling at them like a ghost tugging at a curtain. This idea was proposed not long ago, in 2016, by researchers studying these icy wanderers. They noticed patterns too precise to be random and too unusual to ignore. Their conclusion? Something massive must be shepherding them, guiding their motion from the shadows. Planet 9 is not like the planets we know. If it exists, it lies so far away that the sun is just a bright star in its sky. Its days are cold and empty. Its seasons last centuries. Its orbit may stretch out more than 20 times the distance of Neptune. And yet, despite all our instruments, it remains invisible. If it's there, it could be a gas giant with a thin atmosphere, or a rocky super-Earth cloaked in frozen light. It could have formed close to the sun and been flung out by gravitational chaos. Or it could be a captured object, an interstellar visitor now bound to our system. As of now, we can only guess. Telescopes sweep the sky, simulations grow more refined, but the planet, if it exists, keeps its distance. Perhaps it hides just beyond the reach of our detection. Or perhaps it's not there at all, and we are misreading cosmic coincidence. As you drift deeper into rest, imagine a lonely world wandering in near-perfect silence at the edge of everything we know. A cold companion to our solar system, keeping its secrets in the dark. Planet 9 may be real, or it may be myth, but in its mystery, it reminds us how much of our own cosmic backyard remains unexplored.
ʻOumuamua. In October of 2017, a telescope in Hawaii spotted something unusual moving through the solar system. It wasn't bound to the sun. It wasn't on a looping orbit like a comet or asteroid. It was moving too fast, too straight. It had come from somewhere else. This object was named ʻOumuamua, a Hawaiian word meaning scout or messenger from afar. It was the first confirmed visitor from another star system, the first interstellar object ever observed passing through our cosmic neighborhood. But it wasn't just where it came from that made it strange, it was what it did. ʻOumuamua didn't behave like anything we'd seen before. It had no tail, no visible outgassing, no dust. Yet it accelerated slightly as it left the solar system, as if pushed by something we couldn't see. And its shape, inferred from how its brightness changed, was unlike any known object. Long and thin like a cigar, or perhaps flat like a pancake, tumbling end over end. It reflected sunlight in odd ways. It showed no heat signature. It was silent and left no trail. Some suggested it might be a fragment of a shattered planet. Others thought it was an icy body wrapped in a crust of dust. A few even speculated it could be artificial, an alien probe drifting and dead, or still listening. But the truth is, we don't know. ʻOumuamua was only visible for a short time. It passed through quickly and vanished into the dark, leaving questions behind. No mission could reach it. No second glance was possible. It came, moved through our system, and was gone. As you rest, imagine a quiet object from another star crossing light years of empty space, unnoticed until the very last moment. A messenger without message, a shape without answer. And somewhere out there, beyond the reach of our instruments, it keeps moving, forever alone.
Tabby's star. In a quiet corner of the constellation Cygnus lies a star that behaves unlike any other. Officially named KIC 8462852, it's more commonly known as Tabby's star, after the astronomer who first brought it to attention. To the eye, it looks like any ordinary star, but when studied through precise instruments, its light tells a story that doesn't make sense. Over time, the brightness of Tabby's star dips, not just a little, but by as much as 20%. And these dimming events aren't regular. They don't follow the familiar rhythm of planets passing in front of a star. They are erratic, deep, and long-lasting. Something is blocking its light, but we don't know what. Comets were an early theory. A swarm of icy bodies releasing dust might explain the fading, but the pattern is too complex. Others thought of clouds of interstellar material or strange rings of debris, yet nothing quite fits. Then came a more imaginative idea. What if the light is being blocked by something artificial? A vast megastructure, perhaps, built by an advanced civilization to harness stellar energy. A Dyson swarm, made of countless panels orbiting the star. Most scientists remain cautious. No evidence supports that idea directly, and natural explanations are always preferred. But still, the mystery remains. Years of observation have only deepened the puzzle. The dips continue, without regularity or clear cause. The star doesn't emit unusual radio signals. It doesn't pulse. It doesn't change color in the way we'd expect if dust were the culprit. It simply dims, briefly, deeply, then returns to normal as if nothing had happened. And so it keeps its secret to itself. As you drift into sleep, imagine a distant sun flickering behind something we don't understand. A soft, blinking light across hundreds of light years, reminding us that, even among the stars, there are stories still untold. Tabby's star waits in silence, strange and steady, its meaning hidden in the shadows it casts.
Booty's void. Far beyond the reach of our own galaxy lies a place unlike most others in the universe. It is not a cluster of stars, nor a nebula glowing with light. It is not a galaxy rich with dust or a swirling cloud of gas. It is emptiness, vast, quiet, and nearly untouched. This is the Booty's void, one of the largest known voids in the cosmos. Discovered in 1981, it stretches across hundreds of millions of light years. To put that in perspective, it is as if someone carved out a sphere so large that tens of thousands of galaxies could fit inside, and then left it almost completely empty. It is a hole in the cosmic web, a place where very little seems to exist at all. In a universe filled with structure, where galaxies form long filaments and bright clusters connected across unimaginable distances, the Booty's void is an interruption, a stillness, a whisper in the fabric of space. Scientists have found only a few galaxies inside it, tiny islands of matter floating in an ocean of dark. Why this emptiness exists is still a mystery. Some suggest it's a natural result of how matter clumped together after the Big Bang. Others think it may hint at something deeper, perhaps a relic of the early universe's strange and chaotic expansion. And there are those who wonder if the voids we find are not just empty, but emptied, changed by forces we do not yet understand. As you close your eyes, imagine drifting into the Booty's void. No stars, no planets, no sound, just blackness stretching in every direction. So complete, it feels like a pause in the universe itself. And yet, even here, gravity stirs. Even here, faint light moves. In this quiet absence, we find not nothing, but a different kind of presence. A reminder that space is not always filled with fire and dust. Sometimes, it is the silence between that speaks the loudest.
Cosmic microwave background. Long before stars were born, before galaxies spun and planets formed, the universe was a dense, hot sea of particles and light. In those early moments, everything was opaque. Light could not travel freely, constantly scattered by particles in a glowing, turbulent fog. But then, about 380,000 years after the Big Bang, something changed. The universe cooled just enough for atoms to form, and suddenly, light was free. That ancient light still exists today, stretched by the expansion of space into microwaves, faint and cold. We call it the cosmic microwave background, or CMB. It is the oldest light we can see, a soft glow that fills the entire sky. It is not bright, not visible to the eye, but it is everywhere, an afterglow of creation itself. When we observe the CMB, we are looking back in time to a moment when the universe became transparent. We see not stars, but patterns, tiny variations in temperature, barely a fraction of a degree. Yet those subtle ripples were the seeds of everything that followed. Where the CMB is slightly warmer, matter would later clump into galaxies. Where it's cooler, space would remain more empty. It is a quiet blueprint of the universe. And yet, even in this ancient echo, mysteries remain. There are strange anomalies, cold spots larger than expected, alignments that don't fit with randomness, and asymmetries that puzzle cosmologists. Some wonder if these are statistical flukes. Others think they may hint at new physics, or even imprints from a multiverse beyond our own. The CMB is often called the baby picture of the universe, but it is more than that. It is a silent song, echoing from a time when nothing as we know it existed. No stars, no planets, no memory. Just light, finally freed, now whispering across space. As you relax and listen, let your thoughts drift back through time, past the galaxies, past the silence of the void, to a warm and glowing moment when the universe first opened its eyes. The CMB is that first breath, still echoing, still present, still quietly waiting to be fully understood.
Fast radio bursts. They last for just a fraction of a second, sometimes only milliseconds. A single pulse, a flicker, a whisper of energy that crosses the universe in silence. These are fast radio bursts, or FRBs. In that instant, they can release more energy than our sun emits in days, and we still don't know what causes them. The first was discovered in 2007, buried in old data from a radio telescope. It came from far outside our galaxy, brief, bright, and unexplained. Since then, astronomers have found hundreds more, scattered across the sky, each one sudden and powerful. Some repeat, most do not. They seem to come from all directions, as if the entire universe is occasionally blinking at us. Theories abound. Some believe they come from magnetars, neutron stars with magnetic fields so intense they warp space. Others suggest colliding stars, black holes, or exotic cosmic strings. There are even those who wonder if somewhere in the vastness, these pulses are signals, intentional or not, from intelligent life. But there is no proof, only patterns. We have tracked some FRBs to distant galaxies. We know they pass through intergalactic space, stretching and scattering as they travel. Some repeat with rhythm, others appear once and never again. And despite the instruments we build and the sky we scan, they remain mysterious. They don't warn us, they don't linger. They flash and they vanish. A cosmic heartbeat without a body. As you let go into sleep, imagine a deep black sky, cold and endless, suddenly lit for the briefest moment by a pulse of invisible energy. Somewhere, light decades away, something moved, something changed, and we caught its whisper, if only for a blink. FRBs remind us that the universe is still full of surprises, quiet, distant, and waiting to be heard.
Cosmological principle, Hubble tension. For over a century, scientists have worked under a quiet, elegant assumption that the universe, on large scales, is the same in every direction. This idea is known as the cosmological principle. It suggests that no place is special, not our galaxy, not our view of the sky, not even the distant clusters that shimmer faintly on the edges of our instruments. On average, the cosmos should be smooth, homogeneous, and isotropic. But as our measurements grow more precise, quiet inconsistencies begin to appear. One of the most pressing is known as the Hubble tension. It's a disagreement between two methods of measuring how fast the universe is expanding. One looks nearby, at stars, supernovae, and galaxies, measuring their motion outward using classical distance ladders. The other looks far away, at the cosmic microwave background, the whisper of the early universe, and calculates expansion from models of how everything evolved since the Big Bang. The problem is, these two methods don't match. The expansion rate measured from the nearby universe is faster than what we expect based on the early universe. This isn't just a small error, it's persistent, precise, and growing harder to explain away. Some think this tension hints at new physics. Perhaps dark energy behaves differently over time, or perhaps there's an unknown particle changing the rules. Others suspect subtle biases in the way we observe and interpret light across vast distances. And quietly, in the background, a deeper question waits. Is the universe truly smooth, or are we simply assuming symmetry where none exists? If our place in space happens to be unusual, the principles we rely on may bend. As you settle into stillness, consider this. The universe, vast and ancient, may not be as even as it seems. Beneath its apparent calm, the expansion may shift, stretch, and surprise us. And in those discrepancies, in the tension between two truths, there may lie the next great discovery.
Origins of cosmic magnetic fields. Magnetic fields are everywhere in the cosmos. They thread through galaxies, spiral around stars, drift between planets, and even shape the movement of cosmic dust. And yet, we do not fully understand where they come from. In our own galaxy, the Milky Way, magnetic fields weave through the spiral arms like invisible threads, shaping the behavior of gas clouds and influencing star formation. They extend far beyond what the eye can see, subtle but constant. And they are not unique to us. Other galaxies show similar structures, ordered, large-scale magnetism reaching across tens of thousands of light years. But this order must have come from something. The question is, what? Scientists believe that magnetic fields did not form fully grown. They likely began as tiny fluctuations in the early universe, primordial seeds, faint and chaotic. These seed fields may have been generated by quantum effects shortly after the Big Bang, or from currents in the hot plasma that filled the young universe. But even those explanations remain uncertain. Over time, those weak fields would have been amplified by motion, rotating galaxies, turbulent clouds, the flowing of charged particles. This process is known as the dynamo effect, where kinetic energy is slowly converted into magnetic structure. But for the dynamo to work, the seed must exist. And so the mystery returns. What created the first magnetic breath in a universe that was otherwise smooth? Some researchers turn to inflation theory, others to phase transitions in the early cosmos. Some even explore exotic physics far beyond the standard model. And still, no answer is definitive. As you lie still, listening to the hush of space, imagine these unseen fields stretching across the stars. They guide charged particles, sculpt solar winds, and shape the silent architecture of galaxies. They are not loud, they do not shine, but they are always there, ancient and patient, tracing patterns in a universe that still holds so many secrets.
Galaxy rotation problem.
When astronomers first began measuring how stars move within galaxies, they expected a familiar pattern. Stars near the center, close to the galactic core, would orbit quickly, pulled tightly by gravity. Farther out, the stars should slow down, just like planets in our solar system move more slowly the farther they are from the sun. But that's not what they found. Instead, stars in the outer edges of galaxies were moving just as fast as those near the center, in some cases even faster. This wasn't just surprising, it was impossible to explain with the gravity of visible matter alone. There simply wasn't enough mass to hold those stars in orbit. According to everything we knew, the galaxies should fly apart. This strange result became known as the galaxy rotation problem. It was first noticed in the 1970s, most notably by astronomer Vera Rubin, whose quiet but persistent observations confirmed that something unseen must be at work. Her data showed that spiral galaxies, like our own Milky Way, rotated in ways that defied expectation. The outer stars weren't slowing down, they were racing along, held tightly by something we could not see. The solution proposed was dark matter, an invisible mass that surrounds galaxies in vast halos, extending well beyond what telescopes can detect. This dark matter doesn't emit light, but it exerts gravity, enough to account for the missing force. It changed the way we understand the cosmos. But while dark matter fits the behavior, it still eludes direct detection. And so, even today, the galaxy rotation problem is not just a measurement. It is a gateway to one of the universe's deepest mysteries. As you drift towards sleep, picture a spiral galaxy turning silently in the dark, its arms wide, its stars sweeping through space at impossible speeds, and around it, an unseen halo holds everything together. Not with light, but with presence. A whisper of mass, a gravitational embrace from the invisible.
High-Redshift Quasars. In the deep silence of the early universe, long before galaxies had settled into graceful spirals, there were quasars, brilliant beacons of energy powered by monstrous black holes. Some of these quasars shine from such great distances that their light has taken more than 13 billion years to reach us. We call them high-redshift quasars because the expansion of the universe has stretched their light into the red end of the spectrum. But their distance is not what makes them mysterious. It is their mass. These early quasars are powered by black holes 1 billion times the mass of the Sun, and yet they formed so soon after the Big Bang, only a few 100 million years into cosmic history. That should not be possible. According to what we understand, black holes grow slowly. They begin as the collapsed cores of stars, then feed over time on gas, dust, and matter that comes too close. Even with optimal conditions, it should take billions of years to reach the size we observe in these ancient quasars. But these black holes were already giants at a time when the universe was still young, still forming its first structures. The question is, how did they grow so fast? Some scientists suggest special kinds of black hole seeds, massive ones, born not from stars, but directly from collapsing gas clouds. Others think these black holes may have merged again and again in the dense early universe, feeding in violent bursts. Still, the process remains unclear. There are limits to how quickly a black hole can grow, and these early quasars seem to ignore them. As you rest, imagine the quiet dawn of the cosmos, filled not just with the soft birth of stars, but with sudden, brilliant outbursts, quasars blazing like lighthouses across the void, powered by black holes that somehow grew too fast, too soon. Their light reaches us now as a whisper from the ancient past, still burning, still unexplained.
Black hole information paradox. Black holes are the quietest monsters in the universe. They consume everything that crosses their threshold: dust, gas, stars, even light itself. At their core lies the event horizon, a boundary beyond which nothing can return. And yet, in that stillness, a deep and unsettling question waits. What happens to information when it falls in? According to quantum physics, information cannot be destroyed. The patterns that define particles and their states, what they are, how they move, how they interact, must be preserved, even if reshaped. But black holes seem to defy that rule. When matter falls into a black hole, it disappears, not just physically, but mathematically. The equations that describe black holes care only about mass, charge, and spin. Everything else, structure, composition, detail, is lost. If the black hole evaporates, as Stephen Hawking proposed, through a slow release of radiation, then all that information seems to vanish completely, erased from the universe. And this presents a paradox. Either the laws of quantum mechanics are wrong, or black holes are not what they appear to be. Some theories suggest the information is encoded in the radiation itself, hidden in subtle patterns we have yet to understand. Others propose that it lingers on the event horizon, like a hologram, etched into the surface of space. There are those who speak of firewalls, bursts of energy at the edge of black holes that burn information away, an idea that would shatter everything we know about space and time. And some imagine that information escapes into other universes, slipping through black holes like trapdoors in the fabric of reality. As you close your eyes, let this thought drift with you. Somewhere, deep in the dark heart of a black hole, lies the memory of everything it has consumed. The question is whether the universe remembers too, and if it does, where it keeps the secret. Event horizon firewalls. For decades, black holes were imagined as smooth and silent. Their event horizons, those invisible boundaries that separate the inside from the rest of the universe, were thought to be unremarkable to anyone falling in. If you crossed it, you wouldn't feel a thing. No wall, no resistance, just a gradual drift toward the unknown. But in recent years, this quiet image has been challenged by a radical idea. What if the event horizon isn't smooth at all? What if instead it burns? This is the firewall hypothesis, a theoretical possibility born from the deep contradictions between gravity and quantum mechanics. According to quantum theory, information cannot be lost. According to black hole physics, everything that falls into a black hole disappears. But if a black hole evaporates through Hawking radiation and the information is truly lost, then something fundamental breaks. To resolve this, some physicists proposed a bold solution. Maybe, instead of a smooth passage, the event horizon is a violent boundary, a firewall, a region of intense energy that destroys anything attempting to cross. If this were true, it would rewrite the nature of black holes. No longer gentle at the surface, they would become searing, shredding anything at the edge before it even enters. The idea is controversial. It breaks with general relativity, which insists that an infalling observer experiences nothing special at the horizon. It also challenges the principle of equivalence, one of Einstein's foundational ideas. Most physicists hope firewalls are not real. They would mean that our theories are incomplete and that space-time behaves far more violently than we ever imagined. But the paradox remains unsolved, and the firewall is still on the table. As you rest, consider this quiet mystery, that black holes, so still from afar, might hide not calm but flame, a boundary not of nothingness but of fire, invisible, silent, and waiting at the edge of understanding.
White holes. If black holes are where matter disappears, white holes are where it might emerge. They are the hypothetical opposites of black holes, objects from which nothing can enter, only escape. A white hole would be like a cosmic fountain, pushing matter outward, never inward. While black holes pull, white holes repel. The idea comes from the same equations that described black holes. When extended mathematically, those equations suggest the possibility of a time-reversed black hole. Instead of swallowing everything, a white hole would spit out light, matter, and radiation. But while black holes have been observed indirectly through their gravitational effects and shadows, white holes remain entirely theoretical. No white hole has ever been detected. Still, the concept continues to intrigue physicists. Some wonder if white holes could explain the mysterious bursts of energy we sometimes observe in the sky. Brief, brilliant events with no clear source. Others propose that a black hole's singularity might connect to a white hole somewhere else, possibly even in another universe. In that scenario, the material consumed by a black hole wouldn't be destroyed, but recycled. The black hole would act as a passage and the white hole as an exit. Some theories of quantum gravity even suggest that the Big Bang itself might have been a kind of white hole, an eruption of energy from an unknowable collapse. But for now, these ideas live in the realm of speculation. White holes are beautiful solutions to complex problems, but the universe has not shown us one yet. As you drift towards sleep, imagine the quiet reverse of everything you know. A point in space not that devours, but that gives. A place from which time flows outward, matter spills gently into the dark, and everything that was once lost finds its way back into the light. A mirror to the black holes we fear. A beginning rather than an end. Gliese 436b, hot ice planet. Orbiting a small red star just 30 light-years from Earth is a planet that seems to defy the rules of nature. Its name is Gliese 436b, and at first glance, it appears to be a typical exoplanet, roughly the size of Neptune, with a tight, close orbit around its host star. But this world hides something strange beneath its atmosphere: ice that doesn't melt. The planet's surface temperatures are estimated to be around 300 degrees Celsius, hot enough to boil water many times over. And yet, despite the heat, scientists believe the planet is covered in a form of solid water, hot ice. It's not ice in the way we know it on Earth. It's not cold, not fragile, not melting in the warmth. Instead, it exists in an exotic state, compressed by such immense pressure that water molecules are forced into a solid lattice, even at extreme temperatures. This form of matter is known as Ice 7,
a phase of water that forms only under extreme conditions, like those found deep inside large planets. On Gliese 436b, this hot ice may form a layer around the core, trapped under a hydrogen-rich atmosphere. Despite the burning heat from its nearby star, the pressure is so intense that the ice stays locked in place. The atmosphere may also be escaping, bleeding off into space in a long, ghostly tail as radiation from the star strips away its outer layers. It's a planet constantly shedding, slowly unraveling in the quiet pull of its orbit. As you drift toward rest, imagine a world of impossible physics, a place where ice burns, where pressure freezes the unfreezable, and where water, the essence of life, takes on a form unknown on Earth. Gliese 436b is not a place for oceans or clouds. It is a place of silence, pressure, and contradiction, a reminder that the universe holds states of matter we can barely imagine, waiting quietly in the light of distant suns.
Himiko Cloud. In the deep past of the universe, when the first galaxies were still forming and light had only just begun to travel freely, there existed a massive, glowing structure, unlike anything scientists expected to find. It is called the Himiko Cloud, named after a legendary Japanese queen, and it is one of the most distant and earliest known objects ever observed. Located more than 12 billion light-years away, we see it not as it is now, but as it was just 800 million years after the Big Bang. What we observe is a vast, luminous cloud of ionized hydrogen gas stretching across hundreds of thousands of light-years, far larger than most early galaxies should have been capable of producing. It is glowing with energy, but the source of that energy is not entirely clear. Some believe the Himiko Cloud is home to one or more early galaxies, still merging and forming, pouring out light from newborn stars. Others suggest it could be energized by massive black holes or intense starburst activity. But the sheer size of the cloud and its brightness challenge our models of the early universe. At that time, the cosmos was still dark and dense. Structures were small, and light was often trapped. The presence of such a large glowing region so soon after the Big Bang raises quiet questions about how quickly matter gathered, how stars ignited, and how energy moved through space. There is no other known object quite like Himiko at that distance. As you lie still and listen, picture a glowing veil stretching across a young universe, quiet and immense. A faint light shining through primordial darkness. No stars as we know them yet. No familiar galaxies. Just this single, strange cloud. Alone, ancient, and bright against the silence. The Himiko Cloud is a mystery that speaks in distance, in time, and in light too old to remember its own beginning.
Rectangular nebula. Among the many shapes the universe takes, spirals, rings, bubbles, and clouds, there is one that stands out for its quiet strangeness. It is called the Red Rectangle Nebula, a glowing, geometrically precise formation of gas and dust located about 2,300 light-years away in the constellation Monoceros. What makes it so unusual is its shape. Not round, not scattered, but symmetrical, angular, almost architectural. A red-tinged rectangle, perfectly outlined in soft radiance. It looks like something designed, something deliberate, but it is entirely natural, or at least as far as we understand. At the heart of the nebula lies a binary star system where two stars orbit closely around one another. As one of them ages and expels its outer layers, a dense, slow wind of gas flows outward. This gas is shaped by the gravity of its companion star
and channeled through dusty rings or cones, forming the sharp, glowing edges we see from Earth. Light from the central stars reflects off the dust in just the right way to produce its eerie red glow, enhanced by molecular emissions. But even with models and simulations, the precise symmetry remains difficult to explain. The structure is too clean. The corners are too defined. In a universe known for chaos and curves, the red rectangle whispers of order and balance. Some astronomers believe we're seeing light and shadow playing tricks from a specific viewing angle. Others wonder if magnetic fields or exotic interactions help sculpt its shape, but no one is entirely certain. As you drift deeper into stillness, imagine this distant form suspended in the darkness of space, a glowing red window standing alone among the stars. It does not flash or move or burn with fury. It simply shines softly in a shape nature rarely chooses. The rectangular nebula is a quiet enigma, a structure both simple and unexplainable, gently challenging the curves of the cosmos with its sharp, silent lines.
Fermi Bubbles. High above and far below the center of our Milky Way galaxy, there are two enormous silent structures, ghostly shapes that stretch for tens of thousands of light years into the galactic halo. They are invisible to the eye, yet unmistakable to the instruments that can detect them. These are the Fermi Bubbles, vast balloon-like regions glowing faintly in gamma rays, discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope. They rise out of the galactic plane like twin towers of energy, symmetrical and soft-edged, as if the Milky Way once exhaled in both directions. But no one is entirely sure what caused them. Some astronomers believe the bubbles are the lingering afterglow of a violent event, perhaps a burst of star formation, or a jet of energy fired long ago by the supermassive black hole at the galaxy's core. In this scenario, the central black hole, Sagittarius A, may have flared to life millions of years ago, briefly feeding on matter and ejecting energy into the surrounding space. Others suggest the bubbles could result from streams of cosmic rays or supernova activity, less dramatic but still powerful. Inside the bubbles, high-energy particles race through thin gas, creating faint light in the most energetic part of the spectrum. They are huge, spanning over 50,000 light-years in total, and yet their edges are surprisingly sharp. The uniformity and scale of the bubbles suggest a single coordinated event, but no such event has been directly observed. And so the mystery remains. As you drift toward rest, picture the galaxy as more than just a flat spiral of stars. Imagine it breathing long ago, sending two great clouds of energy out into the dark. The Fermi bubbles remain there still, vast, quiet, and unexplained, like fading echoes of something the Milky Way once did, long before we were here to notice.
Missing Baryon problem. We know what we're made of: atoms, protons, neutrons, electrons. This kind of matter is called baryonic matter, and it forms everything we can touch, see, and measure directly: stars, planets, gas clouds, even ourselves. In the early universe, shortly after the Big Bang, we had a clear prediction of how much of this ordinary matter should exist. Observations of the cosmic microwave background and the physics of light elements told us that about 5% of the universe should be made of baryonic matter. But when astronomers looked into the nearby universe, counting up the stars, galaxies, and gas, they found only about half of it. The rest had vanished, not into black holes, not into dark matter, but simply gone. This became known as the missing baryon problem.
For years, it puzzled scientists. If baryonic matter is made of known particles, where could it be hiding? Gradually, a quiet answer began to form. The missing matter might be there, but spread too thin to see. It may exist not in galaxies, but between them, as part of a vast, diffuse structure called the warm-hot intergalactic medium. This web of filaments connects galaxies across the cosmos, made of gas so sparse and faint that it barely leaves a trace. Detecting it is difficult. It doesn't shine on its own. It can only be found through the absorption of light from distant sources or through subtle signals in the X-ray and ultraviolet ranges. Slowly, through patient observation, evidence has begun to emerge. The missing baryons may not have disappeared at all. They may have simply slipped into the quiet spaces between things, waiting for us to notice.
Cosmological magnetic fields. Across the universe, invisible threads stretch silently through space. They do not glow, they do not move with speed, but they are there, magnetic fields on a cosmic scale, gentle and ancient. Galaxies are filled with them. So are galaxy clusters, the voids between, even the vast filaments of the cosmic web. These magnetic fields influence how gas moves, how stars form, and how cosmic rays travel. But despite their presence, we still do not know exactly where they came from. That is the mystery of cosmological magnetic fields. Did they begin in the earliest moments of the universe, born from quantum fluctuations in the first slivers of time? Or did they arise later, as galaxies spun and stirred the surrounding gas? One idea is that tiny random fields were generated during the inflationary period, an instant after the Big Bang, when space itself expanded faster than light. Those weak fields may have stretched with the universe and settled into its structure, laying the groundwork for the magnetism we see today. Another possibility is that magnetic fields formed through the motion of ionized gas as the first stars and galaxies ignited. Over time, these fields may have grown stronger through the dynamo effect, where rotating and turbulent flows slowly amplify magnetic strength. But the fields are not just strong inside galaxies, they also exist far outside them, where no stars shine and no gas stirs. This suggests that their origin may lie deeper, farther back, and more quietly than we thought. We have only recently begun to map them in detail, using the way they bend light from distant sources and polarize the faint background radiation. As you drift into rest, picture these fields not as lines of force, but as a kind of memory, silent patterns written into space itself. They hold no color, they make no sound, but they are part of the structure of everything, wrapping the universe in a quiet, invisible weave. A magnetic fingerprint from a time before time, still present, still unknown.
G-Dwarf Problem. G-type dwarf stars are quiet and familiar. Our Sun is one of them, stable, long-lived, shining gently for billions of years. These stars are common, or at least they should be. According to models of how galaxies evolve, G-dwarfs should be numerous, especially older, metal-poor ones, stars formed early in a galaxy's history, before heavier elements had time to build up. But when astronomers studied the stars in our own Milky Way, they noticed something strange. There weren't as many of these old, metal-poor G-dwarfs as predicted. In fact, there were far fewer. This mismatch became known as the G-Dwarf Problem. It's not just a missing star or two. It's a quiet contradiction between theory and observation. If the galaxy formed gradually, enriching itself with heavier elements as stars lived and died, then the record of that process should remain visible in the population of stars today. But the expected fingerprints, the metal-poor G-dwarfs, are largely absent. Over time, scientists have explored possible explanations. Maybe the galaxy formed more rapidly than we thought, skipping the long period of low metallicity star formation. Maybe gas from outside the galaxy diluted the chemical mix, masking the pattern. Or maybe stars migrated over time, reshaping the stellar population we see in the galactic disk. Each theory offers clues, but no single answer has resolved the puzzle completely. The G-Dwarf Problem remains an elegant, lingering question, a soft whisper in the data, reminding us that even familiar stars can hide subtle mysteries. As you drift off, consider this. In a galaxy filled with light, it is not just the rare or the distant that baffles us. Sometimes, the mystery lies in what we expect to see, but don't. A quiet absence, written in starlight, still waiting to be understood.
Faint young sun paradox. The sun, like all stars, changes over time. In its youth, it was fainter, about 30% less luminous than it is today. That much is clear from stellar models and our understanding of nuclear fusion. And yet, here on Earth, life began early. The planet had liquid water, rivers, oceans, and even primitive organisms, all within the first billion years. This presents a quiet contradiction. If the young sun was so dim, Earth should have been frozen, locked in a global ice age. But it wasn't. Instead, it was warm enough to support the fragile beginnings of life. This is the faint young sun paradox. The early Earth defied expectation. Scientists have long tried to explain how our planet stayed warm under such a cold sun. One possibility is that Earth's atmosphere was thicker, rich in greenhouse gases like carbon dioxide and methane. These gases would have trapped heat, keeping the surface above freezing despite the weaker solar energy. But estimates of ancient atmospheric levels don't fully support this. Another idea suggests that clouds may have been different, perhaps fewer in number or more efficient at letting in sunlight while still insulating the planet. Some models even propose that the Earth absorbed more heat from space, or that geothermal energy from within played a larger role in climate. There is no single answer, only a soft puzzle woven into the planet's early past. It's also possible that multiple small effects combined, each gently tipping the balance toward warmth. As you rest, picture the young Earth under a pale sky, the sun smaller, softer, but still rising. Oceans ripple beneath it, life stirs in the shallows, and above, the early atmosphere holds in just enough warmth to allow it all. The paradox remains, a reminder that even our own world, so familiar and studied, still keeps quiet secrets from its first days. Olbers Paradox. Look up at the night sky. It is vast, calm, and filled with stars. But it is also mostly dark. This darkness feels natural, even comforting. And yet, when you stop to consider it, the darkness becomes a mystery. If the universe is infinite, filled with stars in every direction, then why isn't the sky blazing with light? Why, wherever we look, do we not see the glow of countless suns stacked behind one another, their light filling every gap? This question is known as Olbers' Paradox.
It was first posed centuries ago, quietly unsettling the idea of a static, eternal universe. If space goes on forever, and stars are evenly spread throughout, then every line of sight should end on a star. The sky, in that case, should be bright, white-hot with endless starlight. But it isn't. The answer lies in the nature of the universe itself. It is not static. It had a beginning, and it is expanding. The light from distant stars hasn't had time to reach us yet. Space stretches their light into longer, dimmer wavelengths. What was once visible becomes infrared, then radio, then silence. The farther we look, the younger the cosmos becomes, and the fewer stars there are. Beyond a certain distance, the sky becomes not dark by chance, but by limitation. There simply hasn't been enough time for all the light to arrive. The darkness, then, is not empty. It is filled with unseen light, still on its way. As you lie still, imagine the night sky not as a void, but as a canvas stretched by time. Its silence is not absence, but distance. The stars are there, scattered beyond reach, their light diluted by the age and breadth of space itself. Olbers' paradox teaches us that even darkness is meaningful, that the quiet between stars holds the story of the universe, still unfolding, still traveling toward us.
Circumgalactic medium mystery.
Surrounding every galaxy, including our own Milky Way, is a vast, nearly invisible cloud of gas. It stretches far beyond the spiral arms, beyond the stars, into the dark where the galaxy slowly fades into intergalactic space. This region is called the Circumgalactic Medium, or CGM. It is not part of the galaxy itself, but it is not separate either. It is the atmosphere of a galaxy, thin, hot, and elusive. For a long time, this region was overlooked. It is too diffuse to see directly and too faint to light up the sky. But over time, astronomers began to suspect that something was missing. Galaxies didn't contain all the matter they were supposed to. There were gaps in the accounting of gas and metals, the elements formed in stars. Those missing pieces, it turns out, were hiding in the circumgalactic medium. The CGM is not just empty space. It is a reservoir of material. Gas that flows in, feeding galaxies and fueling new stars, and gas that flows out, pushed by supernovae and black holes, recycling matter back into the void. It is a quiet but dynamic boundary, shaping the life of galaxies without ever being fully seen. But the CGM is still a mystery. Its structure, temperature, motion, all remain only partially understood. We detect it through its fingerprints, how it absorbs light from distant quasars, how it interacts with cosmic rays, how it glows faintly in ultraviolet and X-ray. Some parts are cool and dense. Others are hot, stretched thin across light years. The balance of these phases, the way they move and change, is still unclear. As you settle into sleep, imagine a galaxy wrapped in a soft, invisible shell. Gentle winds of gas flowing in and out, shaping what the galaxy can become. The CGM is not bright, it is not loud, but it is essential. A quiet, unseen ocean surrounding each island of stars, patiently connecting galaxies to the wider universe and holding secrets just beyond the edge of what we can see.
Missing satellite galaxies. According to our best models of how the universe formed, galaxies like the Milky Way should be surrounded by hundreds, perhaps thousands, of smaller companion galaxies. These are called satellite galaxies. Tiny, faint collections of stars bound to a larger galaxy's gravity, drifting nearby like quiet moons. But when astronomers looked into the night sky,
and mapped the satellites of our Milky Way, they found far fewer than expected. Only a few dozen have been confirmed. This gap between prediction and observation is known as the missing satellite problem. In the cold dark matter model of cosmology, structure forms from the bottom up. Small clumps of matter collapse first, and then merge into larger galaxies. This model predicts that countless small halos of dark matter should surround big galaxies, each one capable of hosting a small satellite. But where are they? One possibility is that the dark matter halos are there, but they never collected enough gas to form stars. They exist in silence, invisible, dark, and undetectable with current instruments. Another idea is that they were once brighter but lost their gas early in the universe's history, perhaps stripped by radiation or galactic winds. Still others may be hidden in the glare of the Milky Way or too faint to detect with past surveys. In recent years, astronomers have begun to find more of these faint satellites, often as ghostly smudges in deep sky surveys. Some may contain only a few thousand stars, spread thin across large volumes. But even with these discoveries, the number still falls short. As you drift toward rest, imagine the Milky Way not as a solitary island of stars, but as a vast hub, surrounded by a hidden family of companions, some shining softly, others completely dark. The missing satellites may not be missing at all. They may simply wait, quiet and distant, just beyond the reach of our current gaze.
Galaxy formation early. The early universe was young, chaotic, and hot. In its first few 100 million years, matter had only just begun to clump together under gravity. Hydrogen and helium filled the void, and the first stars were only starting to flicker to life. In theory, galaxies, vast systems of billions of stars, should have taken time to grow. Gradually, small structures would merge, collide, and gather more gas, building up the massive galaxies we see today. But the universe had other plans. When astronomers looked deep into space, and thus far back in time, they found something unexpected. Huge galaxies, already mature, already massive, existing just a few 100 million years after the Big Bang. Some had already formed tens of billions of stars. Others showed signs of complex structure, disks, central bulges, even early black holes. This shouldn't have happened so soon. There simply wasn't supposed to be enough time for so much growth. The discovery challenged our models. How could so much matter come together so quickly? One possibility is that the early universe was more efficient than we thought, cooling faster, forming stars more rapidly, building structure in dense regions where gravity acted like a magnet. Another idea is that we may be underestimating how dark matter guided this process, helping galaxies grow in hidden halos we can't see directly. Still others propose new physics, exotic particles, early bursts of star formation, or unexpected behavior of primordial gas. Whatever the explanation, the early appearance of giant galaxies remains a quiet puzzle. As you fall into stillness, imagine a young universe already filled with starlight, huge structures growing in darkness, assembling with speed and elegance, in defiance of our expectations. These early galaxies stand like ancient monuments at the edge of time, reminding us that the universe builds not only slowly and patiently, but sometimes suddenly in brilliant, silent leaps.
Supermassive black hole growth. At the center of nearly every galaxy lies a supermassive black hole, millions, sometimes billions of times more massive than our Sun. These enormous objects are quiet engines of gravity, often hidden behind dust, sometimes blazing brightly as quasars. But in the early universe, they appeared with astonishing speed. We observe quasars shining just a few 100 million years after the Big Bang, powered by black holes that had already grown to immense size. This rapid emergence poses a serious challenge to our understanding of cosmic growth. Black holes are thought to form from the collapse of massive stars. From there, they grow slowly by pulling in gas, merging with other black holes, and gradually building mass over time. But this process is limited. Radiation pressure from infalling material pushes back, setting a natural speed limit known as the Eddington rate. Under normal conditions, this growth should take billions of years, and yet these early black holes somehow became giants in a fraction of that time. One possibility is that they began large. Instead of forming from dying stars, perhaps some black holes were born directly from collapsing gas clouds, bypassing the stellar stage entirely. These so-called direct collapse black holes could start out with masses tens of thousands of times greater than our Sun. Another idea is that early galaxies were more chaotic and dense, feeding black holes more efficiently through frequent mergers and unstable flows of gas. Some theories even suggest that short bursts of super-Eddington growth may have occurred, allowing black holes to fatten rapidly in the early cosmos. Yet even with these models, questions remain. How common were such ideal conditions? Why do some black holes grow while others remain small? The existence of supermassive black holes in the early universe is not just an observational surprise, it's a fundamental clue, pointing to processes we have yet to fully understand. They rose early, grew quickly, and now sit at the center of galaxies, holding stars and matter in their silent grasp. Their origins remain one of the most compelling mysteries in cosmic history.
Cosmic string evidence. Cosmic strings are theoretical objects, thin, high-energy filaments that may have formed in the very early universe. Unlike the strings of string theory, these are not made of vibrating particles. They are defects in space itself, topological scars left behind when the young universe cooled and transitioned through different energy states, like cracks in ice as it freezes. These strings, if they exist, would be extremely narrow, thinner than an atom, but immensely dense, with a single kilometer of string outweighing entire planets. They would stretch across galaxies, perhaps across the entire observable universe, moving at nearly the speed of light. Their gravity would be intense but tightly focused. Instead of pulling like a massive object, they would cause space to bend around them in unusual ways. One of the clearest predicted signs of a cosmic string is gravitational lensing. Light from distant objects would bend around the string's edge, creating sharp, double images without the typical distortions seen around stars or galaxies. Astronomers have searched for such lensing events, but so far, no conclusive evidence has been found. There have been hints, brief anomalies in cosmic background radiation, unexplained patterns in deep sky surveys, but nothing that rises beyond speculation. Another possible signal could come from gravitational waves. Cosmic strings may occasionally form loops that snap and release energy in bursts. Some researchers believe that sensitive detectors, like LIGO or future space-based observatories, could catch these ripples in spacetime. Still, the signals would be faint, rare, and difficult to separate from noise. The absence of definitive detection doesn't mean cosmic strings don't exist. It may simply mean they are rarer, smaller, or quieter than expected. They remain a fascinating possibility, relics of the universe's earliest moments, older than any star, older than any structure. If found, they would confirm deep theories about how space and time were shaped in the first seconds after the Big Bang. For now, they remain hidden, theoretical, woven into equations and models, waiting for the universe to reveal its more subtle scars.
BLC-1. In 2019, a radio telescope in Australia quietly picked up a signal, It was narrow, stable, and came from a very specific direction, the area of the sky where Proxima Centauri lies, the closest known star to our Sun. The signal, later named BLC-1, wasn't a burst or a pulse. It was steady, almost like a quiet tone, lasting for several hours at a time, reappearing on different days, and centered around a frequency not typically associated with natural cosmic sources. It seemed to pass some of the basic tests used to filter out interference from Earth-based sources. No satellites, no known transmissions. And so, for a short time, it stirred curiosity. Proxima Centauri is only 4.2 light-years away. It hosts at least 2 known planets, one of which orbits in the star's habitable zone. A steady signal from that part of space raised quiet questions. Could it be artificial? Was this a deliberate transmission, or perhaps a form of technological leakage from a nearby world? Scientists at the Breakthrough Listen project, which focuses on searching for extraterrestrial signals, took the detection seriously, but with caution. Over months of analysis, they studied not just the signal itself, but its behavior, repetition, and structure. Eventually, the excitement faded. Patterns in the data suggested that BLC-1 was more likely a form of terrestrial interference, perhaps a drifting signal from a piece of human technology that had passed initial filters by coincidence. It didn't repeat in ways that would confirm an extraterrestrial origin. It wasn't accompanied by other expected features of a genuine transmission. But even so, BLC-1 was unusual. It was the most promising candidate for an alien signal in years, not because it was loud or obvious, but because it was quiet, steady, and unexplained for just long enough to make us wonder. It reminded researchers how complex our own technological noise has become, and how easily it can mimic something extraordinary. And it reminded everyone else that space still speaks in ways we do not fully understand, sometimes clearly, sometimes faintly, and sometimes just enough to make us listen a little closer.
Fermi Paradox. The universe is vast, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of those stars have planets. Some of those planets are likely to be Earth-like. And if life can arise here, then perhaps it has arisen elsewhere. Given the age and scale of the cosmos, intelligent life should have had more than enough time to emerge, grow, and spread across space. And yet when we listen, we hear nothing. When we look, we see no signs. This silence is the essence of the Fermi Paradox, the contradiction between the high probability of extraterrestrial civilizations and the total lack of evidence for their existence. The paradox is named after physicist Enrico Fermi, who once asked simply, "Where is everybody?" It's a quiet question that remains unanswered. There are many theories. Some suggest that life is rare, that Earth may be one of the few places where biology took hold, and intelligence even rarer still. Others think civilizations may rise and fall quickly, leaving only brief traces lost in time. Perhaps advanced species do not expand outward but turn inward, focused on digital worlds, virtual realities, or post-biological existence. There is also the possibility of self-destruction, that civilizations reach a technological threshold and then vanish by war, collapse, or accident. Or perhaps the universe is not as welcoming as it seems. Maybe the silence is intentional. The zoo hypothesis suggests that we are being observed but deliberately left undisturbed. Another idea is the Great Filter, a barrier that most life cannot pass, either before intelligence emerges or after. And still, it may be simply that the distances are too vast, the signals too faint, the timescales too misaligned. Civilizations may be calling out, but their voices haven't yet reached us or ours them. The Fermi Paradox remains unresolved, not because the universe is empty, but because it remains silent. The stars shine, the planets turn, but the skies offer no answer, only the possibility that we are early, or alone, or simply not listening the right way.
Diffusive interstellar bands. When light from distant stars travels toward Earth, it doesn't arrive unchanged. Along the way, it passes through clouds of gas and dust in the interstellar medium, the vast space between stars. These clouds don't just dim the starlight, they also leave behind fingerprints. In the star's spectrum, its unique pattern of light, astronomers observe dark lines where specific wavelengths have been absorbed. Most of these lines are well understood, caused by known elements like hydrogen, calcium, or sodium, but some of them remain a mystery. These are the diffusive interstellar bands, or DIBs. First noticed nearly a century ago, they are broad, dark absorption features seen in the spectra of many stars. More than 400 have been cataloged, yet the specific molecules or particles that cause them are still unknown. That makes DIBs one of the oldest unresolved puzzles in astronomical spectroscopy. Unlike narrow absorption lines from simple atoms, DIBs are wide and smooth, suggesting they're caused by complex molecules, possibly long chains of carbon, organic compounds, or ionized particles drifting through interstellar space. Some candidates have been proposed, such as polycyclic aromatic hydrocarbons or fullerenes, but none have been definitively linked to the full range of observed bands. The DIBs are faint, and they vary subtly depending on where the light passes through. They're affected by local radiation, by the density of the medium, by magnetic fields, but not in ways we fully understand. These bands appear in nearly every direction we look, suggesting that whatever causes them is widespread and ancient, and yet we still cannot name it. As we refine our instruments and peer more deeply into the fabric of space, the DIBs remain, a quiet code embedded in starlight, a soft and persistent whisper from the space between. Their presence is a reminder that the void is not empty, and that even in the most silent places, there are signatures left behind, unexplained but waiting.
O'Connell effect. In the study of variable stars, those that change in brightness over time, astronomers often observe a rhythm. Many of these stars exist in close binary systems, orbiting one another in tight loops, their gravity tugging and stretching each other, their light rising and falling with each pass. When plotted on a graph, this brightness over time creates a light curve, usually with two dips, one for each eclipse, as one star passes in front of the other. In theory, the two peaks between the dips, when neither star is eclipsed, should be equal. But sometimes they're not. This unexpected imbalance is known as the O'Connell effect. First noted in the 1950s by Daniel O'Connell, the phenomenon shows up as an asymmetry. One of the maxima in the light curve is consistently brighter than the other. This difference is small but persistent. It breaks the expected symmetry of binary star systems and hints at subtle, unseen dynamics. Several explanations have been proposed, but none are definitive. One idea is that star spots, dark, cooler regions on the surface of a star, could distort the light. If a large spot appears near the limb of one star, it might dim the brightness at a specific phase of the orbit. Another possibility is mass transfer. In some binary systems, material flows from one star to the other, forming a stream or an accretion region that glows more brightly and shifts the light curve. This flow could create a permanent hotspot, altering the system's balance. Magnetic activity, tidal distortion, or circumstellar matter might also play a role. Yet no single model explains all observed cases. And the O'Connell effect remains a quiet mystery, small in scale but rich in implication. It reminds us that even in well-studied systems, subtle deviations can persist for decades without a full answer. In the simple pattern of starlight rising and falling, there exists a gentle asymmetry, barely visible, but always there. A quiet irregularity in the rhythm of the stars.
Gravitational wave background. The universe is not silent. Beneath the stillness of space,
Below the silence between stars, there is a hum. Not a sound we can hear, not a signal we can see, but a subtle vibration, like ripples on the surface of a pond that was disturbed long ago. This is the gravitational wave background, a theorized echo of the earliest events in the cosmos. Gravitational waves are distortions in the fabric of space-time itself. When massive objects like black holes or neutron stars collide, they send out ripples that travel across the universe at the speed of light. We first detected such a wave in 2015, a brief signal from a pair of merging black holes over 1 billion light-years away. But beyond these individual events, scientists believe there may be something deeper, an ever-present background of gravitational waves, a soft cosmic rumble from countless collisions and cataclysms spread across the entire history of the universe. This background might include the mergers of ancient stars, the collapse of primeval objects, or even tremors left over from the Big Bang itself. Unlike electromagnetic radiation, which can be blocked or scattered, gravitational waves pass through everything. If this background exists, it flows through you now, through Earth, through the entire solar system, without resistance, without notice. We do not yet know if we can hear it. Instruments like pulsar timing arrays and next-generation detectors are searching, listening for a gentle, consistent signal beneath the noise. Not a burst, not a flash, but a constant, quiet whisper of gravity, shifting the rhythm of time itself. As you lie still, imagine that even space is never fully at rest, that in the deep dark between galaxies, the universe remembers. Not in words or light, but in faint waves passing through all things. A memory of ancient collisions, written not in sound, but in the invisible breath of gravity itself.
Ultra-high energy cosmic rays. Scattered across the sky, beyond the range of human vision, particles move at nearly the speed of light. They come not in waves, but as single, solitary messengers, atomic nuclei flung through space with energies far beyond anything we can create on Earth. These are ultra-high energy cosmic rays. Their energy is immense, sometimes as much as a well-hit tennis ball compressed into a single subatomic particle. No human-made accelerator comes close. These particles strike Earth's atmosphere only rarely, triggering delicate showers of secondary particles as they collide with air molecules. They are detected not by what they are, but by what they cause. For decades, scientists have watched and measured, tracing their direction and impact, but the question remains, where do they come from? Supernovae can accelerate particles to high speeds, but not this high. Magnetars, quasars, colliding galaxies, none of them fully explain the sheer energy involved. One theory suggests they may be born in active galactic nuclei, where black holes at the centers of distant galaxies hurl matter outward through magnetic fields. Others consider the shock waves from galaxy mergers or unknown processes in the early universe. But these ideas remain just that, ideas. The particles themselves are neutral or stripped of identifying charge. Their paths are bent by intergalactic magnetic fields. By the time they arrive, their origin is obscured. It is as if they come from nowhere, bearing only the trace of distant violence. Despite all efforts, their sources remain unidentified. They cross space, silent and fast, reminders that some of the universe's most powerful processes still elude understanding. Their energy speaks of events on a scale we cannot see and forces we cannot yet name.
Naked singularities. At the center of every black hole lies a singularity, a point where gravity becomes infinite, where the known laws of physics collapse into incomprehension. Normally, this singularity is hidden, wrapped within the event horizon, a boundary from which nothing, not even light, can escape. But some solutions to Einstein's equations suggest another possibility, a naked singularity, a point of infinite density exposed to the universe, unshielded by any horizon. If such an object exists, it would defy the cosmic censorship conjecture, the idea that nature always hides its singularities. Without the protective veil of an event horizon, the singularity would interact with space, time, and matter in unpredictable ways. Light could escape from it. Particles could fall in and come back out. Information, normally lost inside a black hole, might emerge again. The very concept challenges the foundation of general relativity. Naked singularities are not confirmed, but they are mathematically allowed under specific conditions. Certain rotating or charged black holes, pushed to extreme parameters, may not form an event horizon at all. The resulting singularity would then be visible, at least in theory. In higher dimensions or within quantum gravity frameworks, the rules become even more flexible. Some theories even suggest that the universe itself began as a naked singularity, uncloaked and raw, before expanding into the cosmos we observe today. But as of now, there is no evidence, no observation, just equations that hint at a window into the unknown, a place where time may break, where causality loses meaning, and where physics itself steps beyond the veil.
Final parsec problem. When galaxies collide, their central supermassive black holes begin a long and intricate dance. Pulled together by mutual gravity, they spiral inward over millions of years, losing energy as they disturb surrounding stars and gas. As they draw closer, this process continues efficiently until a certain point. When the two black holes are about 1 parsec apart, roughly 3 light-years, something unexpected happens. The in-spiral slows dramatically, and in many simulations, it appears to stall. This is known as the final parsec problem. At large distances, friction with stars and gas helps drain orbital energy from the black holes. But as the pair tightens, fewer stars remain to interact with. The region around the binary becomes depleted, and without enough matter to continue absorbing momentum, the system struggles to shrink further. The black holes seem trapped, orbiting each other endlessly, unable to bridge the final gap. Yet observations of galaxies suggest that mergers do occur. We see the aftermath: quiescent cores, gravitational wave signals, distorted galactic shapes. So the question remains, what solves the problem in reality? Some models propose that gas flows, turbulence, or triaxial galactic shapes may help funnel new stars into the depleted region, reigniting the in-spiral. Others suggest that the introduction of a third black hole, or asymmetries in the gravitational field, may break the stalemate. Alternatively, dark matter halos or complex relativistic effects might play a role. It's a problem that sits at the intersection of dynamics, relativity, and cosmology. The final parsec is not just a distance, it is a threshold between theory and observation, between stalling and collapse, between question and answer. It remains one of the quiet puzzles in understanding how the largest objects in the universe come together. Modified Newtonian dynamics. When galaxies rotate, their stars move faster than they should. According to Newton's laws, stars farther from the center should orbit more slowly, like planets in our solar system. But they don't. Their speeds remain steady even at great distances from the galactic core.
This behavior has long been attributed to dark matter, an invisible mass that provides the extra gravity needed to hold galaxies together. But there is another possibility. Instead of adding invisible matter, perhaps we need to change the rules. This idea is known as modified Newtonian dynamics, or MOND. Proposed in the early 1980s, MOND suggests that Newton's laws, while accurate in strong gravitational fields, like those on Earth or near the Sun, might not hold in the extremely weak gravitational environments of galaxies. According to MOND, when acceleration drops below a certain threshold, gravity behaves differently, stronger than Newtonian predictions. Under this adjustment, galaxy rotation curves flatten naturally without requiring unseen mass. The theory has had some success in explaining galactic dynamics, especially in low-surface brightness galaxies and certain dwarf systems. But MOND struggles in other areas. It doesn't fully account for the large-scale structure of the universe, the behavior of galaxy clusters, or the cosmic microwave background. Various extensions like relativistic MOND, or TeVeS, have been developed to bridge these gaps, combining modified gravity with additional fields or particles. Still, dark matter remains the more widely accepted explanation, supported by multiple lines of indirect evidence. Yet MOND persists, not as a full replacement, but as a reminder that gravity, one of the oldest forces described by science, may still hold secrets. The question remains open. Are we surrounded by invisible matter? Or do we simply not yet understand how gravity truly works at cosmic scales?
Mass in GR. In classical physics, mass is straightforward. It measures how much matter something contains, how it resists motion, and how it attracts other objects through gravity. But in general relativity, the picture changes. Mass is no longer just a quantity. It becomes a source of curvature in space and time. It tells space how to bend, and that curvature tells objects how to move. But defining exactly what mass means in this context is more complicated than it seems. In general relativity, gravity is not a force, but a geometric effect. Massive objects curve the space-time around them, and that curvature guides the paths of everything nearby. The more mass and energy an object contains, the more it distorts the surrounding geometry. But here's where the difficulty begins. In a curved space-time, there's no universal background to compare against. Unlike Newtonian physics, where forces can be measured against absolute space, general relativity is inherently local and dynamic. Energy and momentum can be spread across fields, radiation, or the fabric of space itself. Because of this, multiple definitions of mass exist in general relativity, each suited to different contexts. The ADM mass, for instance, is used to describe the total mass energy of an isolated system, measured from a great distance. The Komar mass applies in static spacetimes with symmetry. And then there's the Bondi mass, which accounts for systems radiating energy outward. These aren't just mathematical curiosities. They reflect the deep complexity of trying to quantify something fundamental in a universe without fixed coordinates or universal frames of reference. Even the equivalence of mass and energy, expressed in E equals mc squared, becomes richer in curved space, where pressure, momentum, and even gravitational binding energy contribute to the total gravitational effect. In the end, mass in general relativity is not a single value, but a contextual quantity, fluid, shaped by motion, radiation, and geometry. It's a quiet reminder that the deeper we look into the universe, the less familiar even our most basic concepts may become.
SDSN, Extreme Trans-Neptunian Orbits.
Beyond Neptune lies a region filled with icy bodies, faint, slow, and distant. These are the Trans-Neptunian objects, silent wanderers tracing wide arcs around the sun. Most follow paths that align loosely with the solar system's general plane, an invisible disk formed by billions of years of gravitational shaping. But some objects break this pattern. They move on highly elongated, tilted, or even perpendicular orbits. These are the so-called extreme Trans-Neptunian objects, and their behavior challenges our understanding of solar system dynamics. One example is Sedna, whose orbit stretches far beyond Pluto, with a perihelion that never brings it close to Neptune. Others, like 2012 VP113, show similar traits: odd tilts, strange alignments, and isolation from the known gravitational influences of the planets. These orbital patterns are not random. Some of them appear clustered, their paths pointing in similar directions, as if guided by a hidden force. This has led some scientists to propose the existence of Planet 9, a massive, unseen world tugging gently on these bodies from the outer dark. Its gravity could shepherd them into these unusual orbits over time. But Planet 9 is still hypothetical, and not all extreme orbits can be explained this way. Other theories suggest that early in the solar system's life, passing stars or nearby protoplanetary systems may have disturbed the outer regions, sending objects into eccentric paths. Some even consider that these bodies were captured from interstellar space during the Sun's formation cluster. The exact mechanisms remain uncertain. Simulations reproduce some patterns, but not all. Observational bias may also play a role. Our instruments are limited, and the deep solar system is vast and dim. Still, the data continues to hint at something more. These orbits are the fingerprints of ancient disturbances, quiet echoes of interactions long past. They curve through the outer solar system like questions written in motion, waiting for answers hidden in the dark.
Sednoids Mystery. In the frozen outskirts of the solar system, beyond the orbit of Neptune and even Pluto, there exist a handful of strange objects that defy expectation. They are known as sednoids, named after Sedna, the first and most prominent among them. These bodies follow long, elongated orbits that stretch deep into the distant reaches of the Sun's influence. So distant, in fact, that they appear to lie in a region untouched by the gravitational pull of the known planets. Sedna, for instance, never comes closer to the Sun than about 76 astronomical units, and at its farthest, it drifts nearly 1,000 AU away. Other similar objects, like 2012 VP113 and 541132 ʻOumuamua, show the same detached character, orbits that seem suspended between the Kuiper belt and the inner edge of the Oort cloud, with no clear explanation for how they got there. These bodies are too far from Neptune to have been pushed outward by its gravity, yet too close to be considered true Oort cloud objects. Their paths hint at something missing, a force, an event, or perhaps a hidden planet. Some astronomers suggest that sednoids are the best indirect evidence for Planet 9, a massive, unseen world far beyond Neptune that might have sculpted their orbits over billions of years. Others propose that in the early days of the solar system, a passing star could have nudged these bodies into place, or that they were captured from another system entirely. But the truth remains elusive. Only a few sednoids have been discovered, and their faintness makes them difficult to study. They move slowly, hidden in the deep, dark sky. Their orbits are long, thousands of years from one passage to the next. We catch only a glimpse of their story as they sweep through the solar system's distant edges. They are relics, fossils of a time when the solar system was young and chaotic. Their mystery lies not just in where they are, but in what they might tell us about the forces that shaped our cosmic neighborhood. Quiet messengers from a colder, more distant realm.
Kuiper Belt oddities. Beyond the orbit of Neptune lies the Kuiper Belt, a vast, icy region filled with remnants from the early solar system. This belt is home to a diverse collection of objects, dwarf planets, frozen rocks, and dark, silent bodies drifting slowly through the cold. Most follow gentle, predictable paths,
forming a broad disk aligned with the plane of the solar system, but not all. Among the thousands of known Kuiper Belt objects, some behave strangely. Their orbits are tilted, stretched, or twisted in ways that don't match our models. Some have high inclinations, rising far above or dipping far below the solar system's average plane. Others, like 2004 XR190 or 2015 TG387, follow elongated orbits with distant aphelia that suggest gravitational influences we cannot fully explain. A few are locked in resonances with Neptune, orbital relationships where timing keeps them stable despite potential encounters. Pluto, for example, orbits in a 2 to 3 resonance, completing 2 orbits for every 3 of Neptune. But beyond Pluto, patterns emerge that hint at something more. Certain objects cluster in specific orientations, their perihelia pointing in similar directions. This alignment is unlikely to occur by chance and has led some researchers to propose the existence of an unseen massive body, Planet 9, shaping the Kuiper Belt from afar. Other theories explore early solar system dynamics, gravitational scattering, stellar flybys, or the influence of the protoplanetary disk. These processes could have disturbed the belt long ago, leaving behind a scattered asymmetric population. The oddities aren't limited to orbits. Some Kuiper Belt objects rotate unusually fast or show signs of complex chemical surfaces. Others, like Haumea, are elongated or possess tiny moons, suggesting violent past collisions. Altogether, the Kuiper Belt is not a simple, quiet ring of debris. It is a dynamic, evolving region full of surprises, evidence of a past more chaotic and mysterious than once believed. Each strange orbit is a clue, each object a frozen memory of a solar system still revealing its structure and history.
Iapetus Ridge Mystery. Among Saturn's many moons, Iapetus stands apart. It is small, heavily cratered, and rotates slowly. But what makes it truly strange is the ridge, a narrow, towering structure that runs almost perfectly along its equator, stretching for over 1,300 kilometers. In some places, it rises more than 20 kilometers high, forming jagged peaks that cast long shadows across the icy surface. It is unlike anything else in the solar system. No other known moon or planet bears a ridge like this, especially not one so precisely aligned and so sharply defined. Its presence has puzzled scientists since it was first imaged in detail by the Cassini spacecraft. How did such a structure form? One theory suggests that Iapetus once had a ring system of its own. If material from that ring collapsed onto the equator, it could have piled up over time, forming the ridge. But for a small moon to host and sustain a ring system seems unlikely. Another possibility is that internal forces caused the ridge, perhaps from early rotational bulging when Iapetus spun faster, or from upwelling material beneath the crust. Yet the moon shows little sign of current geological activity. Some propose a more violent origin, a collision with a massive object, or the remnants of a shattered companion moon drawn into a narrow band. Each theory addresses part of the mystery, but leaves questions unanswered. The ridge is old, as cratered as the rest of the moon, indicating it formed early and has changed little since. Its presence hints at a past unlike the stable, frozen appearance Iapetus presents today. It may be a monument to ancient motion, a frozen wave from a forgotten chapter in the moon's evolution, a reminder that even the quietest objects in the solar system can carry scars from histories we don't yet understand.
Saturn's internal rotation. Saturn is a giant of gas and clouds striped with bands of wind and color, spinning with graceful speed. But beneath its atmosphere lies a mystery that has proven remarkably difficult to solve. how fast does Saturn itself rotate? Unlike a solid planet, Saturn has no fixed surface to track. Its outer layers are composed of clouds and fluid hydrogen that flow at different speeds depending on latitude. At the equator, the winds are fast and persistent. Near the poles, they slow. These winds can mask the motion of the deeper interior, making it difficult to determine whether the planet's core turns with the same rhythm as its upper layers or something entirely different. One way scientists tried to measure Saturn's rotation was by studying its magnetic field. For planets like Earth and Jupiter, magnetic field variations can reveal the spin of the core. But Saturn's magnetic field is unusually symmetrical, offering few clear signals. Even data from the Cassini spacecraft, which orbited Saturn for over a decade, failed to provide a definitive answer. Estimates of the rotation period have varied by minutes, an enormous uncertainty in planetary science. Some models suggest the core may rotate faster than the cloud tops, while others propose that deep zonal flows may extend inward, decoupling the layers. It's possible that Saturn's metallic hydrogen interior spins on its own, hidden beneath layers of liquid helium and compressed gases. Understanding Saturn's true rotation isn't just a curiosity. It affects estimates of its mass distribution, internal structure, and even its formation history. Despite centuries of observation, the question remains open. Saturn, with all its grandeur, still guards the rhythm of its heart. Clouds may spin in view, but the core keeps its own quiet time, concealed beneath pressure and depth.
Solar corona heating. The sun's surface, the photosphere, burns at around 5,500 degrees Celsius, a searing temperature by earthly standards. But above it lies something far more puzzling, the corona, a vast halo of thin glowing plasma that stretches millions of kilometers into space. It shines faintly during solar eclipses and flares brightly in ultraviolet light. Yet what makes it truly mysterious is its temperature. The corona reaches over 1,000,000 degrees Celsius, far hotter than the surface below. This defies intuition. In most physical systems, temperature drops as you move away from the heat source. But the sun reverses this expectation. Its outer atmosphere is inexplicably hotter than its surface. This is the solar corona heating problem, and it remains one of the great open questions in solar physics. Several theories attempt to explain it. One involves waves, Alphen waves, rippling through the sun's magnetic field. These waves carry energy from the convective zone below and may deposit that energy into the corona through friction or dissipation. Another possibility centers on magnetic reconnection, where twisted field lines suddenly snap and realign, releasing bursts of energy that heat the surrounding plasma. This process is common in solar flares and may also occur on much smaller, constant scales throughout the corona. But direct observation is difficult. The corona is diffuse and transparent, and the energies involved are hard to isolate. Instruments like NASA's Parker Solar Probe and ESA's Solar Orbiter are designed to study the sun up close, moving through the solar wind and peering into the processes at work. Even with these tools, the full mechanism remains unclear. Perhaps the answer lies in a combination of subtle effects, magnetic loops, wave heating, and turbulent dissipation all working together. Or perhaps there is still a missing piece, an unrecognized aspect of solar behavior waiting to be understood. What is clear is that the corona does not behave as expected. It surrounds the sun like a silent blaze, thin and faint, yet unimaginably hot, challenging our understanding of energy and motion in the star that gives us life.
Solar magnetic cycle. The sun, though it appears steady and constant in the sky, is a restless sphere of charged particles and shifting magnetic forces. Every 11 years or so, its magnetic field flips. North becomes south, and south becomes north. This regular switching is part of the solar magnetic cycle, a rhythmic dance of invisible lines threading through the sun's interior and atmosphere. But what drives this cycle remains a topic of deep investigation. At its core, the sun is a ball of plasma, not solid, not liquid, but a fluid mix of charged particles. It spins faster at the equator than at the poles, a phenomenon known as differential rotation. This uneven motion stretches and twists the sun's magnetic field lines over time, winding them into complex patterns. Deep within the convection zone, where hot plasma rises and cool plasma sinks, this motion interacts with the existing magnetic fields through a process called the solar dynamo. The dynamo theory suggests that this churning motion converts kinetic energy into magnetic energy, amplifying and reorganizing the field over time. As the magnetic lines become tangled and stressed, they can burst through the surface as sunspots, cool, dark regions associated with strong magnetic activity. These sunspots follow a pattern too. They begin near the solar mid-latitudes and gradually migrate toward the equator as the cycle progresses. Eventually, the field becomes so distorted that it flips, resetting the polarity. Then, the process begins again. Despite detailed models, many details remain unclear. Why is the cycle so regular? What causes the occasional weakening or strengthening of its intensity? And why do some cycles seem to vary in length or behavior? Periods like the Maunder minimum, when sunspots nearly vanished for decades, show that the cycle is not always stable. Ongoing missions and solar observatories continue to study these patterns, watching for clues in the sun's light and magnetism. The solar magnetic cycle is more than just a curiosity. It affects space weather, satellite safety, and even Earth's climate. It is a slow pulse within the sun, an unseen rhythm that shapes the behavior of the entire solar system.
Maunder minimum mysteries.
Between roughly 1645 and 1715, astronomers observed an unusual silence on the surface of the sun. Sunspots, typically numerous and shifting over time, all but disappeared. For 70 years, the solar surface remained calm, quiet, and strangely empty. This period became known as the Maunder minimum, named after Edward and Annie Maunder, who studied the historical records and brought the anomaly to scientific attention centuries later. What caused the sun to fall into this prolonged state of magnetic dormancy remains uncertain. The solar magnetic cycle, usually dependable in its 11-year rhythm, seemed to pause or enter a drastically weakened mode. The underlying solar dynamo, the mechanism thought to generate the sun's magnetic field, may have faltered, shifted, or reconfigured itself in ways we still don't fully understand. The Maunder minimum coincided with a stretch of cooler global temperatures on Earth, particularly in the northern hemisphere. Rivers froze that rarely did. Winters grew longer and harsher. Crops failed more often, and historical accounts tell of colder summers and snowfalls deep into spring. This period, known as the Little Ice Age, wasn't caused by the Maunder minimum alone. Volcanic activity, oceanic shifts, and atmospheric patterns all likely played roles. But the sun's diminished output may have contributed, especially through reduced ultraviolet radiation and changes in solar wind that affect Earth's upper atmosphere and cloud formation. The link between solar variability and climate remains an open field of study. We know the sun influences Earth's environment, but the details of how small changes in magnetism ripple through the complex climate system are still being unraveled. The Maunder minimum stands as a quiet warning. Even our star, massive and seemingly eternal, is not immune to change. Its cycles may be stable now,
But they have wandered before, and when they do, the effects may echo far beyond its glowing surface, touching Earth in ways both subtle and profound. FRB Sources. Fast radio bursts, or FRBs, are among the most fleeting and mysterious signals in the cosmos. They last only milliseconds, arriving suddenly from far beyond our galaxy and vanish just as quickly. First discovered in 2007, these ultra-brief flashes of radio waves puzzled astronomers from the very beginning. They were powerful, short, and seemed to come from random points in the sky. Some were one-time events, never seen again. Others repeated, though not predictably. The energy released in a single burst is enormous, comparable to the sun's output over days, compressed into a blink of time. Their origins remain uncertain. One leading theory points to magnetars, highly magnetized neutron stars capable of producing intense electromagnetic outbursts. In 2020, for the first time, a fast radio burst was detected from within our own galaxy, and it appeared to come from a magnetar. But not all FRBs fit neatly into this model. Some occur in galaxies very different from the one that hosts our known magnetar burst. Others repeat, sometimes with structure or quasi-periodic patterns. Some are closely tied to star-forming regions, while others seem more isolated. Alternative explanations include collapsing neutron stars, black hole activity, supernova remnants, or exotic interactions involving cosmic strings or axion-like particles. Each new discovery adds detail and often more confusion. Instruments like CHIME, ASCAP, and FAST have greatly increased the number of detected FRBs, revealing hundreds of examples, some repeating, some not. And yet, no single explanation accounts for all of them. It is possible that FRBs are not one phenomenon, but many, that some are local, others distant, some catastrophic, others cyclical. The sky continues to flash with signals we barely understand, brief and bright, scattered across space and time. They are not messages, but they are information. Tiny signatures of astrophysical extremes that challenge what we know about energy, magnetism, and matter itself.
Wherever you are, and however far you've traveled with us tonight, sleep well. And if you're still awake, or simply curious for more, there's another journey waiting right here on the screen.